Okay, ladies and gentlemen, welcome to this afternoon session. This is a special lecture in the Barcelona Insurance and Risk Management series of conferences that is being held together with the Spanish Association of Risk Managers, AGERS. You can see that we are located at the University of Barcelona, and we welcome all the participants to this workshop at the Risk Research Group. We also welcome many participants who are now viewing this event via streaming and the University of Barcelona television. We also welcome offline viewers. Thank you for your interest in data science. Today we have the privilege to have Arthur Charpentier, who is an expert in the field of data science. And he is also a collaborator of our risk group. Arthur Charpentier is a professor at the University of Rennes in France and also at the University of Montreal in Quebec. He has been working extensively in France and Canada with leading insurers, and he works on the intensive use of big data. He also works on predictive modeling and business analytics. When we were invited together in other events, I had always the feeling that Arthur was very good at communicating the concepts behind statistical learning, the model complexity, overfitting, and the selection of variables in a world where there are many, many variables. The goal today is to bring all these new and interesting tools to risk managers and to actuaries that have to face a new digital area. We thank you, Arthur, for accepting this invitation. He will deliver this lecture, and if there are questions, we will collect the questions from here, from the table, and at the end of the lecture, I will try to group them and ask you the questions so that you can reply. We have a total duration of 1.5 hours to 2 hours, so now the floor is yours. Thank you, Arthur.
Thank you, Montserrat. Hi, everyone. It's a real pleasure to be here. So I'm going to give this talk on data science and big data for actuaries. I put two dogs on the picture because I want to focus on something very important. I'm more working on data science than on big data. Okay, so I will talk a little bit about big data, but I think the issue is not there because sometimes data can be small and still extremely important for actuaries. I mean, when we talk about rare events, it's usually about small data. So small data can be extremely important in risk management, but nowadays there's a lot of buzz about big data, so I'm going to talk about that. But keep in mind that my main interest is on data. It's not on big data, it's really on data and how we can use data in insurance companies and in risk management. Okay, so this is the global agenda for today. So just to introduce briefly myself, so as Montserrat was telling you, so I'm a professor actually in the Faculty of Economics nowadays in Rennes in France. Previously I was working in the Faculty of Mathematics in Montreal. I'm currently in charge of a data science program for the French Institute of Actuaries. So we got this one-year program. So it's for people who already became actuaries and they want to know more about data science. So we got this one-year program, which is quite intense because they got a lot of courses on computational science, on computational languages, on machine learning, and a lot of case studies. So we have this program in France, and I'm in charge of it. I also have a research chair called ActInfo. So ActInfo stands for actuarial science. So ACT is actuarial science. Info is we like this because it's at the same time it's informatica, so it's computational science, but at the same time we like it because it can be information. So it's about how insurance company can use information. So it's really about data. So why insurance company get more data and what can they be doing with that? So it's a topic we're involved in with some colleagues in France. So it's a research share funded by some French insurance company. So they want to know more about segmentation, about using information they can get from insurers and to do something. So it can be for pricing, but it can be also to prevent risks. So it's a share that started a few months ago, so it's brand new. Previously, I was also working, so I've been teaching in many places, but I've been also working as an actuary. So previously, I was working in Paris for the French Federation of Insurers, and I was working as an actuary in an insurance company in Hong Kong, in China, for a couple of years. I also got a PhD. So my PhD is in statistics. So I've been trained as an actuary, as a statistician. So just to focus on this background. So I'm not someone coming from computational science. Okay, so I do work every day with a computer, but I'm not trained in computational science. So it's really using tools I've seen from computational science, but it's not my background. My background is really natural science. I also have a blog for econometrics. So this blog started like almost 10 years ago. So by that time, I took this name because actually I liked it. It was the idea of saying that econometrics is not only about mathematics, because usually when you teach econometrics is really about statistical properties of estimators and things like that. And my point was maybe we can play with data. Maybe we can look at the data, try to build a model, try to say something from the data. So I think nowadays people call that data science. But back 10 years ago, there was no name for that, so I called that econometrics, like econometrics, but just to have fun with data. And I guess most of my expertise on data science is coming from the blog. So it's what I've been playing with over the past 10 years. So I've been getting data from insurance companies, from different places, and playing with them. And recently, well, not that recently, but almost 2 years ago, I did publish a book. So I was the editor of that book, actually, because when they asked me to write a book on that topic, I thought that maybe I could mainly be supervising it and ask clever people to write the chapters, because sometimes people know more some different topics than I do. So I've been asking a lot of different colleagues to write chapters on that book. So it's a book on computational actuarial science. So this is what I've done for the past 10 years, and I'm going to summarize almost everything I've learned on data science and possible applications for actuaries. So first, we need to talk a little bit about data. So data is becoming a real buzzword, and I think a lot of things have been changing recently, because we're going to see that data is not something new, right? We've been collecting data for decades, not to say centuries, but there have always been some data around. Okay, so we all seen data, but I think things have changed in the way we look at the data, because especially in economics. So now I'm in the faculty of economics, and what I've seen is in economics and econometrics, people usually have a model in mind. Okay, so they think of something because the theory behind. It might be on interest rates. It can be on almost anything, on labor. It can be on any kind of topic. And usually people try to find data that might support this theory they have, right? So usually the data is coming just to support a theory, but what people are now doing with data is try to get rid of that theory, just look at the data and try to say something. So it's really getting information from the data without some kind of a priori. So it's not try to prove something with the data, it's try to let the data speak. Okay, so we're going to see that it's not that simple. It's not always working, but actually we can just look at the data and learn something, and maybe use it for something. So there was a very interesting paper in Wired by Chris Anderson about the idea that data will be very, very important in the way we do science, because it's going to change a lot of things, and actually it's changing a lot. Okay, so people are not working on the theory. Now they get the data and they try to do something with that. So it's basically where we are right now, and things are changing very, very fast. So I'm going to give you a brief overview of data over the past centuries and explain why it's becoming extremely important to know about data. I will talk a little bit about IT, because IT is also something extremely important, and we need to know how computer works to see exactly what could be done and what could not be done, and where exactly are the limits. Okay, because it looks like things are going extremely fast, but actually we still have a lot of limits. So we cannot do anything with big data. So it's, we still have some strong limitation coming from computers. Then I'm going to talk a little bit about something that we usually don't see in econometrics and in actuarial science. It's machine learning. So I've been trained, as I told you, in statistics and actuarial science. So I know a lot of things about GLM. Okay, so I've been trained on generalized linear models. I've been using that as an actuary, but I never heard about machine learning before. And it looks like we're doing things very, very close. So I'm going to show you how close it is, what are the big differences between what we do in econometrics and what people are doing in machine learning, try to highlight smart ideas that can be used coming from these people working on machine learning, and how they can help us to improve the models, because obviously we reach a limit with GLMs, okay? Especially when we have quite big data sets, okay? And people from machine learning, they got very good ideas. So we're going to see exactly what they do, what they cannot do, and how we can discuss between two different communities, one coming more from mathematics, one coming from computer science. Then I'm going to briefly show some models, because I don't want to get something too theoretical. So I'm going to get a description of different algorithms in classification. So classification is a very popular topic in machine learning, and we're going to see exactly what they do. Okay, so I don't want to get something too general on loss functions, on complexity or things like that. So I want to give you some very specific examples on problems of classification. And then I want to discuss a little bit about small data, because I still think it's a big issue for insurance companies, because we just ended a first cycle related to Solvency II. Okay, so it took a lot of time in insurance companies. Now I think a lot of people are working on those big data problems, but I still think that people want to know more about the risks. Okay, so it's not only about underwriting, about marketing, about big data. There's always something about small data and risk management related to those rare but extremely expensive claims. Okay, so there are some models coming from small data, and what is extremely interesting is that if you look at the models, they're all coming from Bayesian models. Okay, so we got somehow three kinds of communities, okay, one coming from econometrics, one coming from the Bayesian models and statistics, and one coming from machine learning. And I want to show you how those communities can discuss together. And then I will try to give you a conclusion, because all that is related to statistics somehow, but not really actuarial science. And I think the focus of actuaries is quite different from the one we have in machine learning. Okay, so if you've been playing a little bit on modeling issues, on predictive models like Kaggles. So if you try to play in some Kaggle, okay, so you get a data set and you need to provide a model for some classification or for some price. It's fun, but actually it's not what actuaries are doing every day, right? So in actuarial science, you need to set a price for some risks, but then it's a competitive market, okay? And you have to know what competitors are doing. And we've been doing a very small model, try to put different models together and fight together, okay? Because it's how insurance is working, right? You got different companies that they have different data, they got different models, they got different prices, and then the insured is going to choose one of them, okay? And what we've seen, if we try to replicate this kind of model, that prices will go down. There will be probably a lot of bankruptcies of different companies, because of what's going on this big data area we just entered. So we have a lot of things coming in the next years related to this machine learning and big data stuff. Okay. So the first part is about data. So I just want to give you an overview on data. So data is not something new, right? We can find a lot of things, historical things related to data. So people have been collecting information somehow for not to say the past years, not to say the past decades, not centuries, but really a long time, right? Because they know that if they keep tracks of different information, they can use that. Okay, so it's keeping tracks of things that we've seen to avoid problems. So to see when there will be a flood, when we might have some problems, some big risks, some big fires, and so on. So they keep tracks of a lot of things. So there's nothing new here, right? And actuaries have been involved in this kind of thing, because if you get back to the history of probabilities, actuaries have been working on collecting data, especially on longevity, right? So if you get back to what was done in Northern Europe in the 17th centuries, so actuaries have been moving around, they've been going on cemeteries, look at the graves, look when people get born and when they died, try to see how long they've been living and so on. So a lot of things has been done by actuaries collecting data about longevity, right? So it's something where actuaries have been extremely active over the past 500 years. And then, so we started, so I don't want to start that we started the area of big data like 140 years ago, but actually, when you think about it, when they started the US census, they had a lot of people, like 50 million Americans, right? And they've been doing a census, so they got tracks of all those 50 million Americans, right? But it was written on a piece of paper. So I don't know how useful it was, but actually they keep tracks of everything. And then they started to get some machines to help them, right? So in 1881, they got the first tabulating machine that could be used to reduce the workload of people working on those kind of data, right? So it is big data. I mean, I don't know if a lot of statisticians have been working with 50 million observations, but actually it's big data even for nowadays, right? So that was a long time ago, and they didn't have any computers, right? They got this kind of machine. I don't know what it does. I guess it's only storing data, right? So it's just keeping tracks of everything. So they got cards where they got information. So it's basically storing information. It's not about running algorithm. It's just storing the information. And then we started the area where we had people working on statistics. So I just get back on this survey problem because people started to understand, I guess, close to the US election in 1936, that sometimes it can be interesting to get small samples, and small samples can be even more informative than big ones, right? So it was the big problem of this, on this survey, to know who's going to win the American elections. Okay, so you got this journal, the Literary Digest journal, that wanted to get a poll, so they did send cards to their readers, and then they did get back like 2.4 million votes, right? But it was from a sample that was not representative of the Americans, right? So they got a lot of information, but what they got at the end is some prediction that were completely wrong, just because they didn't get the good sample, right? They got a sample that were people reading this journal, not standard Americans. And at the same time, you got Gallup. So Gallup did a survey. So he didn't ask millions of Americans. He just asked 50,000 people who they are going to vote for. And he ended up with something, so it's a bit far away from the final outcome, but it's much better than what people in this journal have been doing. So from this period, we start to think that maybe we can work with small data. Okay, so we can have surveys. And I guess everything in statistics has been based on this idea that maybe we can get something that was exhaustive. We cannot ask everyone what they think about something. We cannot know exactly what everyone is buying, okay? But we can still make surveys. So basically, we just follow 2, 3, 4, 5,000 people and then or families or companies, and then we get feedbacks. So it's always about sampling. So the fact that we got not an exhaustive data set, okay? We got the smaller small sample, but actually we have theoretical results. Like when n goes to infinity, then we got a good estimator and so on. So everything was based on this idea that we got a small sample that should be representative, right? We still have this problem of representation of the sample with respect to the big population, but we can actually have a lot of interesting information on a small sample. Okay, so this is where everything started, I guess, in statistics. So in statistical models, they got a small sample and they want to say something about that. Everyone was expecting that the sample will go large, that we will reach big data when n goes to infinity, but by that time, they thought that they can still extract a lot of information from some small sample. And then so starting from the census, the US government understood that they got a lot of information. So they started to get some data center. So data centers that we talk about nowadays is not something new, again. So back in 1965, so the US government wanted to get a place where they can store information. Okay, so we can call that data because I don't know exactly what they were storing. Okay, so maybe it was pieces of papers, maybe it was something else, maybe it was related to DNAs, to fingerprints. So it was something more material, but actually they were storing things related to people living in the US. Okay, so they got like 175 million sets of fingerprints. Okay, so it's a big data set. Well, I don't know if we can call that data set, but they got a lot of information about a lot of people. So they started to get those data center quite a long time ago, like 50 years ago. And this is how it looks like. So this is a data center 50 years ago. So you got a lot of people looking at different pieces of paper and so on. So this is what we got 50 years ago. And then we started to get computers. So back in the 70s, people wanted to keep information on magnetic tapes, something like that. So they started to store information, and they started to think about how we can store that and how are we going to use that. So basically, everything was stored. Okay, so we got different users, and they can access to the data. So exactly, we don't know exactly what data is, but we got something stored. Okay, so it looks like we got different data sets that might be connected. This is when we started to get some information about different data sets, right? You can get information from taxes, you can get information from surveys, and then you can link them. Okay, maybe we can have a national identity number so that we can relate one person to exactly one person. Okay, and then we can try to make connections between data sets. Okay, so this is when everything started. This is when we started to think that if we try to link all the data sets together, we can have some huge data. Okay, but that's not new. I mean, it was in the 70s, but by that time it was mainly theoretical. Okay, so we started to get theoretical ideas in computational science related to data sets, how we can store data, and how users can use them to extract information. So we started to get a lot of things. So data by that time, it was the way I've been studying them as a student. It was a simple table. Okay, so we got rows. Rows were different people, different insured, and then we got columns for different variables. So this is old, but actually this is what my students are still learning. Okay, so we store data in a table where we got individual information and we got columns. And I guess everyone in this room is doing the same because we're not very familiar with NoSQL. I mean, we're not very comfortable with using Facebook data, with GPS and so on. We always like to get data set as a table, okay, with individuals as rows and with variables as columns, like we do in econometrics. Okay, so far, this is the kind of thing we like to use. And then we got a lot of models in econometrics, but actually, people have been working also on different topics. And this is what Leo Breman called the two cultures, because when we want to do some models, so if you've been trained as a statistician, you know that you got some, maybe some covariates, some features, some information, and then you put that in a model. Okay, so it can be a linear model, it can be a logistic regression, it can be a Cox model for durations, and then you try to predict something. So predict something that would be Y in econometrics. Okay, and this is the standard data modeling culture that we have in actuarial science. So actuarial science is coming from statistics, which is coming from mathematics, and it's based on this idea that we got some explanatory variable, we got a model, and then we're going to predict something. It can be the number of claims, it can be the life length, it can be the fact that someone is going to get an additional cover, that someone is going to, I don't know, buy something. Okay, so it can be for marketing, it can be for rate mating, it can be for almost anything. But there was a different culture doing exactly the same thing at the same time. So it's this community that now we call that community coming from machine learning. It was those people who thought that maybe we just don't really care about the model, we care about having algorithm that might help us to get predictive models somehow. Okay? So we got some the framework is the same, right? We got some covariates, we got something that we want to predict, but we got a model that is more a black box. Okay, we don't know exactly what's inside, but actually we can still get a prediction at the end. Okay, so it's something that people in computational science have been working with, and the idea we have nowadays is because we're doing the same thing, maybe we can start discussing together. Okay, so it's not exactly two culture, right? I mean, for decades we've seen those two culture evolving, but without discussing together. It looks like we reach a point where we should start discussing together because, as we will see, running a logistic regression is nice, but when you have a huge data set, you cannot do it. Okay, so maybe we can start discussing with people in machine learning and try to see what they are doing, try to get some intuition about what they are doing. Maybe we should use it somehow to get back to our old econometric models and learn from each other. Okay, so it's really a discussion about those two communities. And actually, this is what I see from my students. So nowadays, my students are trained in those two areas because we don't have those mathematical statistic courses on one hand and then computational actual statistics on the other one. Okay, so we try to merge the two together and try to say, okay, you don't have only the math and computers. You can try to make them discuss together. Okay, so it's something that people started to see in economics back in 2000, but it was very, very small community. This idea of big data was mentioned in the paper by Diebold in 2000. Okay. There were some ideas that maybe we have big data, maybe we can start discussing with people working on computational science that have other ideas about big data and try to learn from them. And then we arrived after 2000, and we started to see that not only on research papers, but also in business journals. So everyone was claiming that it was the century of big data, that something big is coming out. Okay, so we have this big data deluge, okay, somehow. So we start to see people not dealing with data from an academic point of view, but also working as practitioners, saying that maybe we can do something with this data. Maybe there might be some value to get from those data. Maybe we can improve our process, okay? We can improve our process for underwriting. Maybe we can improve the process in terms of claims management. Okay, so there might be a lot of things that we can learn from the data. Okay, insurance companies have been storing data for decades, and they come out with the idea that maybe it's time to use that and to get information about garage they have for their motor insurance business. Maybe they can start looking at information they got from the kids and the parents, because sometimes not only insurance company insure the parents, but sometimes they got the kids when they get older and so on. So maybe there might be some information coming from historical information. Okay, so we have now companies that have a big interest in this problem of big data. Okay, so there were a lot of big buzz about this big data thing. Okay, so not only we got more practice, more experience in terms of academic knowledge about big data, we also have some new technology. Okay, so now we can store this big data. We can start using this big data. So it's not only a problem of storage, it's also a problem of having algorithm that can be used for this kind of huge data. Okay, but now we have the technology to do that. So it's really up to actuaries to use this technology to do something with this big data. So it's really where we are right now. So we got a lot of things. There were also some big buzz about those popular 3Vs. Okay, like big data is volume, so we get a lot of data. Variety, because data are coming from everywhere, right? So it can be data you collect when you got some new guy coming to buy insurance company, but also information you can get from satellite pictures, coming from social networks, because you know that some insured has a Facebook page and is publishing a lot of pictures where when he's on holiday or when he's sick. Okay, so we get information about this person. It can be from GPS in their car, so it can be coming from different places. And it's about velocity because it's about the speed. So how do you want to use this? How fast do you want to use this kind of data? Okay. So I don't want to talk about high frequency trading because it's not really the topic for today, but it's not playing on a microsecond level. It's really playing maybe on a weekly basis. Like you got more information coming from someone. Can you use it fast enough? Okay, can you take the information you got from the data you can observe and do something with that on a short period of time? And so on. There is also a very important topic in health insurance. So health insurance is probably the most challenging area for actuaries to play with those big data. I mean, if you think about it, so there's nothing new here because we've had a lot of information coming from, not people, but from social networks to predict disease. Okay, so there was something extremely popular, which was the Google flu trend, that was extremely interesting to predict possible flu epidemics. Okay, so it was working extremely well, and then there was a problem. Then they started to get a problem because it didn't predict correctly the flu event. Okay, so I don't know if you know why they got the problem, but actually it's coming from an inside problem. It's coming from the fact that in Google, I think it started 3 or 4 years ago. When you start to type something in Google, then Google is predicting something, right? So when you start typing 3 letters, then you got a word that is going to appear for you, and you have to click just to choose it, right? So it's a very different way of using Google. So you do not type sentences completely. Nowadays, you just start something, and then you got a model behind that is going to predict what you want to say. And then it's like when you have some self-prediction, it's going wrong, right? So it was predicting things wrongly. And then we started to get big differences between the prediction coming from Google and what was actually observed on the database. Okay, so it was working well until we got this endogenous problem coming from the fact that prediction was actually based on predictions. Okay, so we got this loop, and it started to go wrong, right? But the challenge for the future is not predicting those diseases and predicting based on very standard models on time series. It's more coming from the fact that nowadays we can get data from people. Okay, so they can get connected bracelets, so we can get information about their heartbeats almost all day long and so on. So we can know exactly where they are, what they are doing. We can get some pictures. We can get some radiography. We can get data coming from everywhere from people. Okay. So this will be a big question for insurance company, especially with respect to private information. So we start to get problem about privacy. Okay, so what people want to share, what people are ready to share. So what we can observe actually in Europe and in the US is insurance company can collect a lot of things because most of the time they pretend that if you share information with your insurance company, then you will get a decrease on your premium. So basically, give us information and you will get a discount. So a lot of people are saying, yes, you can get information from me, but I guess there is a big bias on who's ready to share information with their insurance company. So I guess insurance companies start collecting data, but there is a huge bias problem in the data they are starting collecting. But anyway, I guess within the next 5 or 10 years, there will be a lot of discussion with respect to this problem of privacy and Internet of Things data set coming from what people are ready to share with their insurance company. I should also discuss a little bit about computational issues, but I guess I will be a bit fast. All the slides can be downloaded from my website, so if you want to know more, you can just download them. But it's just some IT problem that I guess not only actuaries should be aware of, but also about what CEO in companies should know about, because everyone is saying that big data is really a new thing, and we can do almost anything with big data. But actually, it's not the case, because yes, we can store larger data set. Yes, we can run algorithm faster, but still, there are still some physical limits, and there's almost nothing you can do about that. Okay, so if you just think about this, so basically in a computer you got 3 areas, like you got the CPU. Okay, so the CPU is the heart of the computer. Then you got the RAM, which is usually where you store data when you want to run some econometric regression. And then you get the hard drive. Okay, so the hard drive is the hard disk you might have outside your computer, or it can be a bit far away, it can be even in a data center. Okay, so you got the three components. The CPU is where actually you're going to run the code. Okay, so it's going to be extremely fast, but you cannot store a lot of things. The RAM is fast, but extremely limited. And then you get the hard drive. So it's going to be, it might be big, but it's going to be extremely slow to access. Okay, so we got a big trade-off between big data and fast computation. Okay, so it's basically what I'm telling you here. So when you try to read some data set, okay, so I'm just reading very simple data set, like you got one big file of 100 megabytes, then it's going to take about a second. But if you split it in many different small files, then it's going to be as long because you need to access those small files, read them, extract the information, and so on. So all of that is going to take time, and there's nothing to do about that. There are some issues about the cloud, about those data centers where you store things, but so far what I've seen is people are still working on their computer, right? So you still have a computer like this one, and you try to do something with that when you're actually working in a company, right? Sometimes you might have access to a server where you can try to parallelize some code, but most of the time you're working on a simple computer. And you have some big limits on those. I mean, even if the computers we have nowadays are much faster and much bigger than what we had 10 years ago, but still, I mean, if you got a big data set, like 2 terabytes of text file, if you just want to count different things like spaces, reading a 2 terabyte text file is going to take you 6 hours. And there's almost nothing you can do about that. Okay, so it's going to take time to read big data sets. So even if you get big GPS data sets, it's going to be extremely long to read all of them. Okay, so even if we can do things we were not allowed to do like 10 years ago, it will still take a lot of time to do it. And people are now working on how we can improve this time. How can we be faster? But still, computers cannot be that fast. So we can still parallelize. Okay, so parallelization is a big issue on computers, but there are a lot of things going on computational science because you still need, so basically the idea, maybe I could just skip this part and focus on this problem of MapReduce, because this is what actuaries are now doing. You try to split the work. Okay, so you got a big data set you want to read. So basically you get different computers when you can run things. Okay, so you're going to split the work, then you're going to map it, then you're going to run the code, then you're going to reconcile. Okay, so you're going to reduce everything. So you got the mapping and the reducing part, and then you got the output. So this is what people are doing, but still it's taking a lot of time. It's going to take a lot of resources in terms of computational science. Okay, so this is where we are right now. And the thing is, yes, we can get a lot of data, but still it will take some time to read all those data sets because we keep collecting things. And I don't see how we can be that fast. Some things were coming from the idea of using the GPU, so using the graphical processing cards. But still, I mean, it's improving. Okay, it might be interesting, especially on variable annuities, like if you want to generate scenarios. So Monte Carlo can be nowadays quite efficient because you can just run some codes. But Monte Carlo has nothing to do with big data. Okay, so Monte Carlo is just running simulations. Okay, so it's more about generating scenarios. It's not about storing data, storing big data, collecting them, running some process on them. So it's really about generating scenarios. Okay, so it's a very different problem. But I guess Monte Carlo can be nowadays done very efficiently. I mean, this is what we can see from the financial markets, from companies that they have a very interesting codes to run a lot of scenarios that can be used to price complex products like variable annuities. Okay, using Monte Carlo simulation. But again, it has nothing to do with big data because you don't use a big data set that you want to sort. You want to extract information from it. So it's basically generating scenarios, so running some codes, and it's not exactly using data to do something with that, right? And the other thing is data is also very popular because, I mean, you read a lot of things about that every day in the newspapers because it's It's related to artificial intelligence, about what's going on in terms of programming. Like translation. So I don't know if you've been, well, I guess you all use Google Translate, but as you can see, it's working quite well. I mean, for those who've been playing with this kind of thing 10 years ago, trust me, it's working very, very well. It's also what we can see from games. I mean, if you've been following a little bit what happened with Google and the game of Go, right? When they beat the master player of Go with the machine, everything is coming from data, like translation. And things have been changing in the way I was mentioning at the beginning, which is the way we look at data. Okay, so we use data now to get information from that. And this is what people are doing in computational science. So basically, this is a classification problem, right? You get a picture, and you try to say what it is. Okay, so you get a cat, and you get a dog, and you want the computer to recognize which one is the dog and which one is the cat, right? So the idea we got, like, I don't know, 30, 40 years ago was we need to learn, well, we need to make the computer know what a cat is and what a dog is, right? So we're going to explain exactly how a cat is built, how a dog is built, and then he's going to look at it and see, okay, it looks like a cat because they got a big difference on the posterior side here. And so it's really explaining physically what is the big difference. And this is what people were doing in translation. Like if you want to translate from French to Spanish, you need to understand clearly how both languages are working and so on. So it's really a problem coming from, well, people in linguistics were involved in that, right? The thing is, things have been changing because people thought now we can use data. And the idea is maybe we can get some huge data set with pictures of cat, huge data set with pictures of dog, and then it's just having a distance between one picture and another one, right? So we try to see within this set of cat pictures and this set of dog pictures, which one looks more like this one. Okay, so if this one is close to this data set, then it might be a dog. If it looks close to this one, it might be a cat, and so on. So it's basically having a lot of information and just use it. And basically, this is what Google is doing with Google Translate. It's just using some big data sets of text where you got official translation. Okay, so back in Canada, we got those, so it's a two-language country, so we got French and English. So we got a lot of text, but we got at the same time French and English. So when I type something on Google Translate in French, it's going to see if within all the information he got from Canada, if he can find some text where we get exactly the same sentence. And basically, we got exactly the same in English. So it's more complex than that because it's mainly about correlation. So we try to find correspondence between one text and another one. But it's really related to this idea of not learning a language, but trying to find some connection and small distances between things. So this is what people in computational science call a program. So a program is going to give you got an input and you get an output. And this is what in natural science we call a model. Okay, so you got some input, right? So you get information about the car of the insured, you get information about where he lives, about maybe historical information about claims, and then the program is going to give you a price, right? So it's about modeling issues. It's really what we do as actuaries. And the thing is, people in machine learning are also doing exactly the same thing because they understood that the best way to get good prediction is not to learn the process of how everything is working. It's not about causality. It's more about correlation, which is exactly what actuaries have been doing for the past 100 years. Okay, so this is exactly what we are doing. So we are nowadays in this period where we understand that we have to play with those data. We can do a lot of things from them. Okay, so this is exactly what is mentioned in this Dilbert cartoon. So we have a lot of data, right? So insurance company get a lot of data, and actuaries are like, wow, great, we can do a lot of stuff we learned in mathematics and like do some nonlinear mathematics, optimization, and so on. But the problem is we have to convince CEOs that it might be interesting because some of them don't know the difference between a model and spam. So basically, it's just try to explain what we are doing as actuaries, why we can use math to get some good predictions, and trying to explain that, yes, we can improve a lot of things with data sets, with what we can collect from different places, so from insured, but also from almost any kind of places, and use that in an insurance context for predictions. So it can be for pricing, but it can be also for claims management to try to find places where we got problems, like garage, where we get problems when we send cars. It might be interesting to detect fraud and so on. So it can be interesting for a lot of reasons. Okay, so we have to find what we want to do with those data. So just to explain a little bit more what's going on within the actuarial community between statistical models and machine learning, I should just mention, so maybe some of you have been reading this article by Alvayan. So Alvayan is working for Google, so he's an economist. I mean, if you've been studying economics, you might know these very popular textbooks on microeconomics. So he was working as an economist, as an econometrician, and then he was hired by Google, and actually he's been experiencing exactly what I've been experiencing, which is I've been trained as an econometrician, and then I started discussing with people in machine learning that now are hired by insurance companies, and we see that we try to do the same thing, but we got very, very different language. And this is obviously the problem we got when we start discussing with people in machine learning, which is we come from very different backgrounds. Obviously, we're doing the same thing, okay? So in machine learning, they want to predict something, okay? So it's about predictive modeling. They have some covariates. So basically, they don't call that covariates, they call that features, okay? So you get some features, and you try to predict. Most of the time, you don't really care about patterns, okay? So you just want to get a good prediction, and you don't really care about inference. You don't really care about possible changes. So the thing that we do a lot in econometrics, like elasticity, what happens if you change 1x? So if you had +1 to 1x, what happens in terms of y and so on? So it's not what people are working on machine learning. So machine learning is more like, can you get some good classification for zip codes? Okay, so you got zip codes, so you get handwriting for numbers, and you try to read that. So you get something that looks a bit ugly, and you want a model that is going to predict that it's a 3, it's not an 8. Okay, so you want a prediction and classification based on numbers. So this is machine learning problem. In econometrics, actually we got the same kind of problem because we got some covariates that might be interesting to use to predict something that we find interesting. Okay, so if you think in terms of insurance, so you want to predict the number of claims that someone is going to have when you know the gender, when you know the age of the driver, you know where that person lives. Okay, so you got a lot of different variables, and you try to predict something. So it can be a number of claims, it can be the fact that someone is going to get a claim, it can be the fact that this person is going to get a low deductible. Okay, so it can be a lot of information about any kind of variable. And the thing is, even if we do econometrics, which is basically looking for correlation, we always think that there might be some causal issues. Like, we got the intuition that the age might explain somehow the frequency of claims, right? Young drivers get more claims because obviously they are young drivers, right? So they don't know well rule, they don't get a lot of experience. Experience is something extremely interesting and very important in driving. Okay, so when you don't have enough experience, yes, you might have more claims, right? So we got the intuition that there might be some causal effect between the age of the driver and the frequency. And this is why we got this big discussion in Brussels about the gender directive, which is telling us that the gender has nothing to do with claims occurrence. Okay, so there are a lot of discussions related to this problem of seeing a correlation as something that can be used for some kind of discrimination, okay, so for different prices. Okay, so we really care about these possible connections and patterns that we can find between variables. And we like to get this explanation, I guess mainly because actuaries have to discuss with people in underwriting, right? So if you build up a black box and tell them this is the price, they won't buy it. Okay, so you need to explain why you might be using some information you get from other data sets. Okay, so we need to explain to the management why we use this variable for pricing. Okay, but the thing is, because these two communities are doing basically the same thing, maybe we can start discussing with that, with those people. Okay, so this is what Alvayan was telling in his paper about machine learning and econometrics, which is machine learning can help us to learn about new tricks for econometrics. Okay, so we reach, I mean, there's something like 60, 70, 80 years of experience in econometrics, it looks like we can start discussing with people in machine learning to learn new things about what we are doing every day. Okay, so it's really a discussion with people in different communities. There is still a big discussion because I guess the discussion can go both ways. Okay, so as actuaries, we want to discuss with people in machine learning, but I guess people in machine learning would be interested to discuss with people in econometrics, because historically, machine learning, the people in machine learning, they got a data set, okay, but it's very difficult to use it if it's not a good data set. What I mean is, if you got a selection bias when you get this data set, people in machine learning are not very familiar with this problem. It's a very common issue in econometrics. Like, we know about sampling bias, okay, so we know how we can correct from it, this selection bias, but people in machine learning, usually they don't really care about that. It was also the case for non-IID data, okay, so basically in econometry, in machine learning, you like to get independent observations. Sometimes in econometrics, we got temporal observations, okay, so we got time series. And historically, machine learning had nothing to do with time series. So we start discussing together just to share some kind of information. So basically, in econometrics, we really care about how we get those data and where this data is coming from. And people in machine learning, they got very good ideas about what we can do with those data. How we can get a very efficient algorithm to get good predictions, even better than all the one you can get as an econometrician. Okay, so it's really a discussion about this. There is also a big discussion about supervised and unsupervised techniques. So basically, in econometrics, we really care about supervised models. Okay, so we really want to get a prediction. Okay, so we want to predict something. So supervised means we have an interest in some variables. But there are also a lot of things that can be learned from non-supervised techniques that usually we don't see a lot in actual science. So it's related to getting clusters, okay, making groups of variables, making groups of clients. So it's really a discussion that we can have with people in machine learning. So non-supervised models are very interesting. At some point, they were studied in statistics. 50 years ago, in statistical textbooks, you can find things about PCA. But from what I've seen in different programs in actual science, people don't see anything about PCA, right? Because it was, I don't know, I guess it's the way programs in actual science have been designed. Okay, historically, there were a lot of things in statistics, and then things started to get so complicated in finance that we got more and more courses in finance. So basically, they had to drop some courses. So hopefully, they didn't drop all the courses in linear algebra, but some parts on PCA was dropped. But it looks like it's somehow very, very interesting. So PCA is the idea that sometimes you can summarize information you got with a lot of variables in only a couple of components. Okay, so when you have 100 observations, 100 variables, maybe only 3 of them is important, right? Those will be called the 3 principal components. Okay, and this was, I mean, there's nothing new here. This was done most of that was done in the 60s or 70s. But the thing is it's directly connected with big data, right? So it's the idea that when you have a lot of variables, a lot of them will be correlated. So basically, you can just get rid of some of them because most of them are telling you the same story, right? So when you got 1,000 variables, maybe you want to summarize it in a couple or maybe 10 variables. Okay, so it's what we see in PCA. So PCA is really this idea that maybe we have big data, but actually we don't care about all those big data. So we can just care about those principal components. And so I'm just going to skip the math because it's a very general talk, but actually this is what we can see on mortality, right? So this is an application, Robin Mann has been working on that. So Robin Mann has been working on forecasting models for the past 20, 30 years. And he wrote some R chapters, some R packages on forecasting models. And a couple of years ago, he published a package on demography. Okay, so the idea is that maybe we can extract information we got from historical demographic data sets. And this is mortality we can observe in France. Okay, and we can use that to detect outliers. Okay, so in France, we can observe that we got some outliers. Okay, actually, all of them are coming from the wars. Okay, so we got the First World War and the Second World War. So you might think that, yes, it's obvious to detect outliers, but the thing is, we can use that for generating scenarios. Okay, so if you try to generate scenarios for mortality, you might expect to get some outliers too. But if you don't get outliers, it looks like your model is not working well. So we can use this kind of model not only to look at the past, but also to say something about the way we have model generating possible scenarios for the future. Okay, so we have a lot of things that we can learn back from people working on those non-supervised statistical models. It's also interesting when you think about clusters. So cluster models is not about reducing dimension in terms of variables. It's about reducing dimension in terms of individuals, right? So PCA tells you if you got 1,000 variables, maybe you can use only 20 of them. Okay, so 20 variables, you can build them. That can be interesting. Cluster analysis is more, you got 1 million clients, maybe you can split that in different groups. Okay, so it's really about making clusters of individual. And again, that's nothing new because Bertin published a very interesting book in French about those connections between individuals, right? So this is what we can learn from very standard R packages, okay? So we can get connections between people, okay? So it's something that hierarchical clustering is something that was popular 50 years ago, and I guess no one in natural science is learning that anymore. I mean, maybe at least 3 or 4 years ago. And it's something that you can find in different areas. So this is coming from, this is a dendrogram, so maybe you've seen that. It's about regrouping people. So you might say, okay, those two are very close, so I put them together in the same class and so on. So you build classes. Okay, so you're going to regroup them together. Okay, so here we end up with 3 different groups. So it looks like 10 is an outlier. Okay, but you can put that in this kind of graph. So this kind of graph, I don't know if you guys are working on if you like animals, but if you look at some papers dealing with animals, this is how you define classes of animals. Like you say, okay, a wolf is very close to a dog, a cat is very close to a lion is not very close to a bear, and so on. So you try to make groups of animals. Okay, so this is how people represent that in biology. In natural science or in statistics, we prefer the standard cluster dendrogram, right? So this is something that was popular a long time ago. We can see things coming from mixed models. Okay, so the idea that we have a mixture. Okay, so data is coming from a mixed model. So we got one cluster, another one, but we don't know where the cluster is coming from, right? So we don't have possible explanatory variables. So we just try to say, okay, this is coming from 2 distributions, right? So we got the sample coming from 2 distributions, one Gaussian there, one Gaussian there, and we got 2 underlying distributions. So try to get the number of clusters is something very important. So this has been popular in natural science. So I've seen a lot of articles in finance, especially, try to get information about possible clusters, like clusters in volatility, like you got periods where you don't have a lot of viability on the stock exchange, periods where you have very, very big viability on the stock exchange and so on. So you try to get a cluster between different periods of time when you have different states of high and low volatility. Okay, so this is something that people have been saying in actual science for the past years. And you got something coming from the k-means. Okay, so you're going to look at, you're going to get some clusters between individuals. So this was a problem coming from computational science of getting groups of people. So try to put together individuals very close in some set. Okay, so it's a technique that has been popular a long time ago, 60 years ago, but there's a big issue in terms of curse of dimension. Okay, so I'm going to skip this part. There are obviously a lot of things that we can learn from people working on non-supervised technique, but also on supervised techniques. So, what we know as actuaries is coming from regression. Okay, so I guess one of the first course we have as actuaries is this course on econometrics, where we try to predict something based on some covariance. Okay, so in statistics, we just try to get some inference. Actually, statistics is usually a parametric statistic courses. Okay, so we try to get information about parameter. Okay, so we try to estimate the possible number of claims if you assume that you get a Poisson distribution, but that's it. And then with econometric, you start to learn that maybe you can improve your prediction with some covariance. Okay, And this is the starting point of what we are doing in practice, which is this idea of regression. Okay? So if you look at some textbook in regression, it's clearly explained that regression is a problem of conditional distribution. Okay, so you try to get, so you get some data. So in econometrics, we always claim that we get data, even if afterwards we just do math, but actually we just don't look at the data, we just try to get some theoretical results about possible distribution of beta hat. Okay? Then we need to get some assumption about conditional distribution. Okay, so you get your variable of interest. This is clearly some supervised model. So you get the variable of interest y, and you want to know how it's going to vary when some covariates are different. Okay, what is the possible number of claims when you have a woman? What is the possible number of claims you can get when you have a man? Okay, so you got two different Poisson distribution. Okay, and you try, so this is basically the idea of GLM. GLM is really related to this idea of having a conditional distribution. So y given x has a distribution. So this is exactly what we have as a starting point in regression model. So just to show you what a model can be, a regression model can be, so this is a regression model. Okay, so we got y, which will be a function of some covariates. Okay, the function can be almost anything. Okay, and then we got some noise. Okay, so we should never forget about the noise, because the noise is something extremely important. It's something that we cannot get rid of. Okay, especially if you think about rare events like bodily injury. Okay, so it's extremely difficult to predict the cost of a bodily injury claim because it's extremely noisy. Okay, there's a lot of things coming from purely randomness. Okay, so it's something you cannot predict. Okay, so the noise is basically what you cannot predict when you try to get a model. Okay, so you get possible explanation coming from some covariates, and then something coming from the unpredictable. And the problem we have this big data is people might think that actually we can get rid of this epsilon, of this noise, and having more variables actually can get you a perfect model. But obviously it's not what will happen. Okay? It might help us to improve the models, but there will always be some errors in this modeling process. Okay? And the starting point of Econometrics 101 is basically, so M can be a complex function, okay, a very difficult one with a lot of bumps and so on. So we're going to take something linear. Okay, so the linear model is basically this one. So Y will be a linear model of the covariates, and then there will be some noise. Okay, and epsilon will be something that you cannot predict. It's the noise. What we can learn from people working on statistical learning is that sometimes we don't really care about asymptotics, right? So most of the work that was done in statistics and econometrics is about having an estimator, okay, and try to get properties of that estimator when n is going to infinity, right? So if you think about your first course on mathematical statistics, the first thing you see is how can you define, so you see a lot of things about the estimator. You're going to see things about the bias, you're going to see things about the variance, and then the first thing you're going to see is the maximum likelihood estimator. Okay, so we just say, okay, this is a good way to define an estimator. We actually don't know how it behaves, right? But we have a lot of interesting properties, but only asymptotic. Okay, so we know that under some technical assumption, we will have an asymptotic normality. We know that asymptotically it's the best estimator you can get. Okay, so we have a lot of properties on this kind of estimator, and we like it, and usually that's good, that's enough. The thing with people in machine learning is that usually they don't really care about this asymptotic property. Okay, so what they claim is maybe we should start thinking about the fact that maybe we get only 100 observations. Can we get a good estimator for this 100 estimation? So this is basically also the idea that you can find in non-parametric statistics. Okay, so people working on Bootstrap, they raise the same question, like, I don't really care about having a good estimator asymptotically. Okay, I have only a small data set. I want something which is performing not that bad on this small data set. And when you start thinking about that, usually you don't have any mathematical properties because the math is ugly, it's very difficult to get. So basically it's just running simulations, Bootstrap, and you will see that it's coming from algorithm. So when you try to get some good algorithm, you can get generations of possible data set, which we'll call Bootstrap, and then we can compute estimators. We don't know exactly how they will behave asymptotically, but at least with a finite sample, they're not that bad. Okay, so this is an idea that is extremely important. The problem with this kind of technique is it's very difficult to say that it's good if you test it on the same data set you've been using to train your model. Okay, so we got something that is extremely important in statistics in this statistical learning community, which is something that actually I never learned as an econometrician, which is we have to split the training and the testing data set. Okay, so we have to train the model on a training data set, and then if we want to claim that it's good, we have to test it on another data set. Okay, and it's really about predictive modeling. We don't want a good model for our data set. We want something that will perform good next year on another sample, which is basically what actuaries are doing every day, right? So if you build up a model with your data set, you expect that actually it will be good next year when you implement it on new insured. Okay, so it's really about predictive modeling. It's really about having a model that will behave well on another data set. Okay, so it's not being good on a given data set, it's being good in terms of prediction, right? So this is a problem that people in machine learning have been working with over the past 50 years, but that came up very lately in econometrics. And something else is usually in econometrics, so we got the parameter. So parameter is the beta we want to estimate, like in regression. Okay, when you run a GLM, you want to know the estimator of the parameters. And the thing in machine learning is you don't have only parameters. You got also a lot of different things that will be called tuning parameters or meta parameters. So it's something that is not really involved in the estimation. It's something that is always out there that will be related to smoothing. Okay, so you might assume that because you don't want a linear model, you want something more general, but you don't know how general it is. Okay, so you need to get those tuning parameters, and because they cannot be seen as parameters, we don't estimate them the same way. Okay, so basically all of that is also seen in statistics. Okay, there's nothing new here again, but it's something that people in machine learning have been working with probably more than we've been working with as statistician and econometrician. Just to mention one example, so it's something that is known in extreme value theory. Like if you think about it, so in extreme value theory, you're trying to get the tail of the distribution. Okay, so you're trying to estimate the power in the survival distribution function. Okay, so like psi, and if you want to fit a Pareto distribution on the big fire losses you got in a portfolio, you need to focus only on those big losses. Okay, so extreme value is working well, but on extreme values. Okay, so it's working well on very large claims. So you cannot fit a Pareto distribution on all the claims you got in fire business because you got very small claims. Extreme value theory is working for large values. Okay, so basically you need to assess this value of K. So it's basically how many claims you keep as big losses, right? So all the theory in extreme value is based on this idea of either a threshold, so it can be U, or it can be the number of claims you're going to keep as extremes. So all the theory is based on this idea that we got something which is not exactly a parameter, it's a meta parameter. Okay, so the parameter is this tail index, right? But we got also some meta parameters that will be important in the estimation, but are not exactly parameters. Is the number of claims you're going to see as big, or the threshold above which you're going to say, okay, this is a big loss, right? So it's U or K. So U and K can be seen as meta parameters, and we don't really estimate them, right? So estimation has something to do with parameters and not with those meta parameters. So just to show you, this is health estimator. Okay, so we got the psi. So psi is my parameter. Okay, we put a hat. Okay, but we got this meta parameter and we don't know how to fix it. So we call that this Goldilocks principle because it's like in this Goldilocks story we tell to the kids. So Goldilocks is this blonde girly girl, and in the story with the three bears, like you get the big bear, the medium bear and the small bear, and she tries the soup, and it's first one is too hot, the second one is too cold, and then the third one is good. And it's always like that in statistics. There's always a trade-off. It has to be small, but not too small. It has to be big, but not too big. Okay, so we want K to be big, because if it's big, then we can have a lot of claims, right? So if K is large, because we're taking a mean, then it's good, because we got a lot of information. So when K is big, we got a lot of claims. So we got good estimators about the mean. The problem is if k is large, we don't care about big losses. Okay, so on the other one, we want k to be small. But when k is small, that's good because you reach the tails of the distribution, but basically if you got only 20 claims, it's very difficult to do statistics. So it's really this problem of trade-off between having something big and something small at the same time. So it's always in between. Okay, so it's not that small, it's not that big, it's somewhere in between. And in machine learning, they got a lot of techniques to quantify this optimal value. So we're going to put some stars because it's an optimization problem, like we do in statistics, but basically we don't estimate k, we're going to optimize k. So it's a different problem. It's also something that you can see in smoothing problem. Okay, so you want to get a regression here. Okay, so we got observations. It looks like it's not linear. Okay, so it's going up and down, and then it looks like, actually this is simulated data. So actually I know exactly what the model behind is, but we want to estimate it, right? So we're going to use perhaps some kernel regression. Okay, but if you think about that, the kernel regression, we have this bandwidth parameter. So bandwidth parameter is how do you define a neighborhood? Okay, so we want to estimate this regression model. So the regression has to be the expected value somehow, right? So we want to know where we might be when we got a new observation around 4. So what is the expected value of y given that x is close to 4? And this problem of close to is related on the definition of the neighborhood. How big do we want this close to be? Is it small? If it's small, it's good because it means you got a local prediction which is going to be good, but actually we got a lot of variability. Okay, so when h is too small, you get a lot of variation. So you might say, okay, it might be bigger, but in that case, it will be extremely smooth, but very far away from the true value. So it's not too big, not too small, somewhere in between. Okay, so this is clearly something that can be solved with some optimization problems. So we just need to specify exactly what we're looking for, right? So it's really this Goldilocks problem. And again, I told you that this is not new, okay? So try to find this problem, try to solve this problem has been done in statistics for years, and it's not a parameter again. So, okay, so we don't have h hat. Actually, we have a star because it's an optimized value. So we need to minimize some quantity, right? So it's usually based on some loss, okay? So it can be the square loss. It can be some integrated square loss. Okay, so we have this quantity that we want to estimate. So we're going to look for the optimal h. But when you look back in statistical textbooks, you will find formulas like that one. Okay, so this is what you can see in non-parametric statistics. Like, let's do some asymptotic theory. Let's try to find some approximation of this mean integrated square error. Okay, try to do the math, make some expansion, use Taylor's expansion, and then you will get some possible optimal value. Okay, so this is the optimal value you should get for the h function. Okay, so it should be related to the number of observations, but basically it's related also to the derivative of the model value, of the model function. So it's interesting, but it's useless because we need to get those quantities to get this optimal value, but we don't know it. I mean, we don't know m. The problem is we do everything because we don't know m. We try to estimate it. So how can you claim that you know the derivative of m if you do not know m? So it's nice, but actually it's more like a rule of thumb. Okay, so basically with this kind of model, you know that it might be up to a constant like n power minus 1 over 5. Okay, so this is what we have in statistics, which is nice. I mean, if you like mathematics, it's nice. It's a lovely theory, but actually it's asymptotic. It's based on a lot of things, and maybe it's not what you look for in practice. So people working on computational statistics that I will relate to machine learning people, they've been using Bootstrap, they've been using cross-validation. So they've been using algorithm actually, just to say, okay, I don't really care about very general properties of h. I just want an algorithm which is going to tell me, okay, based on this data set, use h equal to, I don't know, 1.17. Okay, so I want something extremely practical. I want to do something with my data set. So I want an h which is going to be optimal for my data set. I don't care about these very general statistical properties, especially when I got some small data, right? So the thing is, it's not only an idea that we should come up when we think about small data. Maybe it's something very general you can use with any kind of data set. Try to find an algorithm that will give us an optimal value, not asymptotically, not based on some mathematical approximation, but that should be efficient and can be computed efficiently quite fast. So a lot of things is related to simulation. Okay, so simulation is something that you all know about because Monte Carlo technique have been popular, especially in finance. So Monte Carlo is something that you know, like if you got observation, okay, you try to fit a parametric distribution. So this is what people in finance like to do. Okay, you got observations, you want to replicate that. So basically you fit a distribution, and then you just draw for that. Okay, so how do you draw from a given distribution? So basically you use the quantile function, the quantile function. Okay, so you just use some observation that were randomly drawn from the unit interval, and then you use the quantile function to get new observations, right? So this is how we perform some Monte Carlo technique, right? So you get a sample, you fit a distribution, and then you just draw from that new distribution, right? So this is the parametric Monte Carlo technique that everyone has been using, especially in finance. The thing is, when you use Monte Carlo, basically it's model-driven. Like, if you don't fit a good distribution, then it's a bit useless because you will get a data, some new data set, right? When you try to sample, you create new data. Okay, so you get one sample of data, but basically you want to create more to see how something is behaving when you get more data or different data. So you fit a distribution, but if it's not in the good family, then it's useless. You draw something which is not good. So something that might be more interesting is maybe we can use not a parametric model, but a non-parametric one. Okay, so basically if you just feed the standard cumulative distribution function and you draw from it, what you can observe is basically you just end up with observation you get in the data set, right? So when you try to use Monte Carlo technique without any assumption in terms of model, so if you just use data, what you end up with is what we call bootstrap. So because what you do here is you just actually resample. Okay, so when we draw from this non-parametric cumulative distribution function, you just end up with some observations you got. Okay, so here you got one chance over n to take this one chance over n to take that one chance over n to take that one, and so on. So basically you end up with all observations with one chance out of n. So basically it's just resampling when you replace all the observation each time. Okay, so this is bootstrap. So bootstrap is just a very natural idea of doing Monte Carlo simulation without any model assumption. So it's really use your data to say something, to do something, right? So bootstrap is based on this idea that we can resample to create new possible observations. So if you know a little bit about claims reserving, this is exactly what we do in claims reserving, right? So when you say we're going to use a Poisson regression in claims reserving to estimate the IBNR, you don't use confidence interval you get from GLM, because usually you get a small triangle, you don't have enough observation to claim that you're going to use asymptotic theory, so basically you just resample your triangle. Okay, so you just regenerate some possible observation for past payments. So you'd use bootstraps to create new samples, see how your best estimate is behaving, and then you get a confidence interval or some quantiles based on the best estimate for the amount of reserve. So bootstrap is something that is also very popular in actuarial science, and it's coming from this idea that maybe we can get something that is data-driven. Okay, it's not driven by a model. So it's really the idea of working with data. If you think of Bremen's two cultures model, we clearly are here in this idea of having an algorithm that will give us some results and not a mathematical problem. Okay, so this is what we're going to use. And this is, bootstrap is something that we use a lot. If you've learned about that in statistics, usually we see the jackknife before. So jackknife is the idea that we got an estimator. Sometimes it's not behaving very well. I mean, there might be a bias. Okay, so if you want to reduce the bias, you can use the jackknife. And jackknife is a very nice idea. It's just what happened if you just take away one observation. Okay, so you get a sample with n observation. You just remove the first one, and you get one observation based on the n minus one last one you got. And then you take off the second one. So you just get back the first one, and you remove the second one. You get another estimator. You remove the third one, you get another observation, another estimator, and so on. So you just repeat that a lot of times, and then you just average this model, right? But this idea that we got in those old textbooks in statistics called jackknife is exactly what we do in this leave one out cross-validation technique we have in machine learning, right? So it's like, if you want to get a prediction for one observation. So you got the highest observation. You just remove it from the sample. You fit a model and try to see how it behaves without this observation. So it's something that can be seen as an alternative to this training, validation, sample thing. Okay, so it's not like remove one half of the observation to train the model and then see how it behaves on the second half. It's like keep everything, but when you want to get a prediction, don't use that observation to see if it's working well. So remove it from the sample you got to train the model and try to see how the model is behaving when you try to make a prediction. So this is this one, leave one out cross-validation technique, popular in machine learning, but it's very close to what we do in statistics in Jackknife, right? And this can be improved as Jackknife has been improved to Bootstrap, and we have a lot of things coming from this Bootstrap theory in machine learning. Okay, so we can get a lot of things, the very different techniques that we can see in machine learning. The first one is the holdout that I didn't mention. So you split the sample in two. So you got the training and the validation sample. So this was nice from a theoretical point of view, but in practice it's very difficult because you don't want to waste observation. I mean, even if it's not really waste, but you try to do that. And then they came up with this one, leave one out cross-validation. But this is complex because if you do properly this leave one out cross-validation, when you got 1 million observations, basically you have to train 1 million models. So it can be time-consuming. So the idea is maybe you just don't do leave one out, but maybe you can leave out some observations. Okay, so you just split the sample in different subsets, and then you're just going to compute these quantities. Okay, so you just remove the first 10%, feed a model on the other 90%, and then get a prediction of the first 10% based on the 90% observation we've been removing. Okay, so this is a way to compute these quantities. This is what people are doing in machine learning, like you got a loss function. So the loss function is something extremely important in machine learning, which is how you're going to quantify the error you're going to get in the model. So what could be the difference between what you actually observe and what the model has been predicting. Okay, so this is what we are doing in machine learning. Okay, so we're trying to compute the sum of all the losses you got on the data set. Okay, so you can improve, well, you can compute that not on the validation sample, but on when you keep everything, you just have to remove it when you do the estimation, and then use that for another estimation afterwards. Okay, so you can have the k-fold cross-validation, you got the leave one out, and so on. You can have the bootstrap. Okay, so you just bootstrap your sample, and each time you don't have observations that were not in your bootstrap sample, then use that as a prediction. Okay, so there are a lot of connections between this bootstrap and this training validation sample technique. Okay, so people in machine learning have been working on this problem. I'm going to show you afterwards why it's necessary to have this kind of quantity, because if you want to get an estimation of the expected value of the loss function, you cannot use the same data set. Okay, because if you do that, you're going to get some overfit, right? So it's really related to this idea of overfitting. There are some big differences between statistical learning and standard statistics. If you look at Friedman, so Friedman published a very interesting book on modeling issues, and he claims that there are different stories you can have when you have a data set. The first one is the one we usually have in econometric, which is you got some covariates, okay, and then you got a mapping between the covariates and the variable you're interested by, okay? So it can be covariates like the age of the driver, the age of the car, where this person is living, and the number of claims this person is going to have. And then there will be some noise. Okay, so basically you just get some possible explanatory variable, then you got a mapping, and then you add some noise around it. Okay, so this is basically how we can generate data set if you want to do some econometric models. Then you have this idea of having a conditional distribution that I've been mentioning before. Okay, so basically you say that y given x has some conditional distribution. Okay, so this is how we define GLM. So GLM is coming from this idea that y given x has a conditional distribution. And then you can get an interpretation for m that may be related to the conditional expected value. Okay, so it's not about causality, okay? It's about conditioning. So there's a big difference between conditional model and Bayesian techniques and conditional distributions. And then you got what you can observe in Tukey's book. So Tukey has been working on explanatory data analysis. And the idea is maybe you can tell a story from the data. You don't need to specify the model. You get data and you just want to get something with that. Possibly you want to explain one variable, and in that case, you're not going to define a model in terms of distribution. Actually, my feeling is that machine learning is not based on the probabilistic space. You don't need a distribution. You don't need to assume IID variables. You just need to say we got a model. We got a data set. And then if we want to predict something, we just need to minimize the loss between what we observe and what we predict. Okay, so it's really about a loss function. Machine learning is about loss function, and econometric is related to distribution. But the two are very close. I mean, if you try to formalize all that, in machine learning, so you got some data. You don't know exactly where they come from, but you got a data set, and then you want to get a model. So the model is something where you try to minimize the sum of the losses you're going to get between what you actually observe and you try to predict. Okay, so this is a machine learning problem. So you specify your loss function. So think of the square. Okay, so this is the least square problem. Okay, so we try to minimize the square of the loss between what you observe and what you predict. Okay, and this is a machine learning problem. We don't need to assume anything about the data set. We just want to minimize the sum of the losses. And when we do some statistics, we always, in econometric, we always start with, assume that you got a probability space. Okay, so you got observations that were drawn from a random variable. So y is coming from a random variable. Okay, and all those variables are assumed to be IID. Okay, so you can relax the assumption if you have time series, but usually when you start the course in statistics or the course in econometrics, you assume that everything is IID, possibly given some covariance. And then you go to distribution. And then, if you get back to statistics 101, you're going to use maximum likelihood technique. Okay, so you're going to maximize the logarithm of the likelihood. So you're going to maximize the sum of the log of the distribution of y given the covariance. So you got something like that. Okay, so if you think about that, actually we're solving the same problem, except that we don't specify it the same way. In machine learning, you specify a loss function. In econometric, we specify a distribution because we assume that we got random variables behind. And then we try to maximize the log of the density, right? But if you think about it twice, maybe you might think, okay, in some cases, we're doing the same thing. Like if you think that f is a Gaussian distribution, then if you take the logarithm of the Gaussian distribution, you end up with this problem when you have a square loss function. Okay, so basically solving the standard linear model when you have a Gaussian distribution is exactly the same as solving a least square problem. Okay, so basically the two communities have something in common. They're working on the same thing, except that there's, I guess, a very fundamental difference coming from where the data is coming from. So I guess all the stories is coming from where you got the data from. In machine learning, you don't really have to specify possible random variables behind, okay? And in econometrics, you do. And we're going to talk a little bit about classification afterwards, but if you read textbooks in machine learning and classification, when you have two possible states, it's usually -1 + 1. Okay, so it's a negative positive problem. In econometrics, usually it's 0, 1. And it's 0, 1 because 0, 1 is when you have a Bernoulli distribution. So I guess a lot of things is coming mainly from notation, mainly from the way we define things in econometrics. And this is where we got the differences in these two communities. Maybe I will skip this part. So a lot of things is coming from this loss function. So the loss function, the good thing is there are a lot of connections between the loss function and things we might be interested in statistics. For instance, if you take the square, the popular quadratic loss, okay, so if the loss function is the square of the error, so between the observed value and the model, actually you end up with something that you might know, which is the expected value. Okay, so when you try to minimize the sum of the square, so this is the sum of the square in terms of empirics, you end up with the average value. If you try to do that on the more theoretical stuff in probability, when you try to find the quantity that is the closest one to a random variable for the square loss, you end up with the expected value. Okay, so I guess if you think about it, this is something that is extremely important for actuaries because the expected value is what we call the pure premium, right? So when you try to compute the pure premium, it's exactly the same as solving a problem where the loss function is the quadratic one, right? So there are really a lot of connections between what actuaries are looking for, which is exactly this quantity, and what people in machine learning are doing when they have this quadratic loss function, right? So we have a lot of possible connection between the two communities. But we can change the loss function. Okay? Another popular one is when you take the absolute value. So when you take the absolute value, actually you get this median value. Okay? And the median is nice because so if you take this sample, so you get a lot of observation here, you get some observation there. If you look at the standard least square regression, you end up with something which is a bit useless. Okay? You end up with this red line. So this is the standard least square problem. You end up with something which is in between. Okay? So it's neither good nor bad. It's just in between, right? So if you take the blue line, the blue line is obtained when you have this absolute value loss function. At least you got something which is performing not that bad on this sample. Okay, so you just remove, so the idea is if you remove these outliers, basically you end up with something which is better. So outliers and the choice of the loss function are extremely correlated. But you can, if you think about that from an historical point of view, so the quadratic loss function was studied intensively by Gauss. Okay, so this is what we learn in econometrics because we can solve it, right? Because we can do the math and because we can take the first order condition. But actually, the blue line, the one with the absolute value, was introduced before. Okay, so Laplace suggested to use this absolute value before Gauss. The problem is he ended up with something that he cannot solve from a mathematical point of view. So the big problem with this, so historically, people found that more interesting. Okay, the problem is when you cannot do the math, then you end up with something a bit different. But actually, we can solve it nowadays. Okay, we can solve it because from a numerical point of view, nowadays we have techniques to use to solve this equation. Okay, so again, when we think about it, when we have computers, we can start solving problems we could not solve before, even if we thought previously that it was more interesting. So computers are extremely important to solve things that could not be solved with standard mathematical techniques. Okay, so it's something that we should keep in mind. We can change the loss function. Okay, we can do a lot of things. We can have the quadratic. We have the absolute value. We can get quantile regressions. Okay, so quantiles are interesting. I mean, if you study obesity, okay, you're not interested about the average weight of people. You focus on quantiles. Okay, so when you want to focus on quantiles and not the expected value, okay, so if your interest is not in pricing but it's more on risk management, maybe we can get a lot of information with those quantile regressions. Okay, and we have also techniques to smooth it, like the Uber loss function. In classification, it's a little bit different. In classification, there are a lot of functions that can be used. And the thing is, sometimes it might be related to the way you define your classes. So in econometrics, in the logistic regression, we got 0, 1. In machine learning, we got the -1 + 1. Okay, so we have differences in terms of notation. Okay, but we got very, very different also functions that we can use. The most common one is the misclassification rate. So how many times did we get a prediction that was not the good one? Okay, so if you think in terms of sick, not sick, okay, how many times do you predict that someone will be sick but actually is not sick, and so on? So you get the misclassification rate, but you can get very different loss functions. And if you try to play with that, each time you change the loss function, you end up with very different stories. So the good thing in econometrics is usually we have only one loss function, like we use a logistic regression, but we might think of the probit one. Okay, so it can be a way to think of this problem. But in machine learning, they got different loss function, and then they will get different predictions. Just to mention a little bit about big data. So in big data, we have this problem of complexity of the model. Okay, so you have a lot of covariates, and we will end up with very complex model. And it is also something that we can see in standard econometric model. So if you think of the least square regression, so we end up with this model. Okay, so y hat, the predicted value for y, can be seen as, so it's usually a linear function of the covariate, but you can also write it as this. So you get this hat function. Okay, so actually it's a matrix that you do apply to your observation. Okay, so a prediction can be seen as a way to reshape observation you got, and this will lead us to a linear predictor. Okay, so we got a linear predictor when the prediction is a linear function of the observation. Okay, so within this framework, actually, you can see a lot of things. Like if you take some smoothing techniques, okay, so any kind of smoother, you can still see it as a linear predictor. Okay, so when you have some smoothing techniques, so if you assume that the frequency of the claim is related to the age of the driver, but it's not linear, okay, so you're going to smooth it, then you need to explain how complex is this model. Okay, so it's not a polynomial function, because in that case, the complexity will be the degree of the polynomial. It's something that is a function that is nonlinear. And we need to define the complexity of this model. Okay, so it will be related to this S function. So basically, if you look at it, if you look at the book of Rupert, for instance, the trace of this smoothing function is what we call the equivalent number of parameters. And this is what we will call the complexity of the model. Okay, so a model is complex when it has a lot of, it's not exactly a lot of explanatory variable, because it's something more complicated than the explanatory, the number of explanatory variable. It's also about smoothing, it's about nonlinearities. Okay, so we need something more general than just counting the number of observations. Okay, so we have techniques in econometrics to take into account the fact that we want to avoid overfit. Okay, so if you think about that, so again in econometrics 101, you define this R square. Okay, so the R squared is nice, but it's not something that you can use to select a good model. Okay, because usually you just add some covariates and you increase the R squared. So usually R squared is a bad measure because it's overfitting. Okay, so there's a great book by Beck. Beck published a book on I guess it's something like machine learning for econometrician, and he called that unjustified optimism. Okay, so it's like you think that you got a good model because you got a great R squared, but it's not good because it's overfitting. Okay, so it's going to include all the covariates you're going to add in the model, but basically if you got a new data set, it's not performing well. Okay, so it's a problem of what people in machine learning call generalization. Okay, so it's having a good model, but not on the data set you have, it's about having a good model on a new data set. Okay, so if it's good on your data set, it's called unjustified optimism. Okay, it looks good, but it's not justified. And people in econometrics have been using the adjusted R-squared. The idea of the adjusted R-squared is try to penalize it. Try to penalize the R-squared, because if you got a complex model, the complexity can be related to the number of parameters or the trace of the smoothing function. Okay, so we have a lot of connections between the two. So we're trying to make a penalization because we want a good model, but not too complex one, because if it's too complex, then we got some overfit. Okay, so we have this idea of penalizing quantities we want to minimize. Okay, so this is what can be formalized in statistics with the AIC. Okay, so if you try to compare model, you don't compare the likelihood, because if you do so, if you add more variables, you're going to end up with a better model. Well, looks like a better model, because if you add more variables in the model, you increase the log likelihood. But basically, you need to penalize for it, because if the model is too complex, then it's not going to perform well if you got some new data, right? So the AIC is based on the idea that maybe we can penalize it. Okay, so we have this log likelihood, but maybe we should penalize. So there is a discussion between the AIC and BIC on the how do you penalize it. But this is what people are doing in statistics. Okay, so we try to solve this log likelihood problem, and then we try to make some penalization afterwards when we do some comparison. And I think it's nice, but people in machine learning have been doing something that I find a bit odd as an econometrician. So in econometrics, you might all heard about this Goodhart's law. So Goodhart says when a measure, any kind of measure, if any kind of measure becomes a target, it's no longer a measure. And the thing is, in machine learning is, people have been saying, okay, if you want to use that to assert that you got a good model, maybe you should not optimize the log likelihood. You should optimize this quantity. So people in machine learning have been saying, instead of solving this problem of solving the likelihood, maybe we should try to solve a penalized likelihood. Okay, so we're going to change a little bit what we're looking for. So we're not going to fit a good model and then penalize it at the end to get a good indicator. We're going to work directly on this indicator. So do exactly what Goodhart has been claiming, which is try to focus on the measure, try to minimize it, and then maybe you will end up with a good model. Right? So this is something that is related to Occam's razor. So it's the idea that you don't want something too complex. Okay? So you want to end up with a model that is simple. It should be good, but also simple. So you got always this trade-off between having something good and something simple. And this is what people are doing in machine learning. So instead of minimizing the loss or the expected loss between what you observe and what you predict, you're going to get a penalty function. Okay, so this is what people are doing in machine learning. It's working on this penalized likelihood. Okay, so the great thing with this technique is actually you might end up with a good model, not on what you observe, but on a new data set. Okay, and this is probably the most important graph in machine learning, which is how prediction is working when you have a complex model. So if you increase the complexity of the model, you can always get a better model on the training sample. Okay, so this is the blue line. The blue line says if you get a more complex model, the error is going to decrease. Okay, so you're going to decrease this blue line. But this is not what we're looking for in predictive modeling. We don't want to get a good model on the data set. We want to get a good model next year on the new clients. And this is what we want to get on the validation data set. And usually what happens is we got this U-curve. So if you start to get a better model, a more complex model, actually you're going to get a better prediction. So it's going to decrease. And then after some point, it's going to increase. Right? So this is something you can always observe. I don't know if I got the animation behind, but this is what you can observe every day on different data sets when you run simulation. Okay, you can always improve the model on the training data set, but it's not what we look for when we do predictive modeling. We want to improve it on the validation sample. And we always end up with a model which is not too complex. So it's always the Goldilocks principle. The model should not be too simple, but it should not be too complex. It's somewhere in between. So the problem is to find this good value of having a good model. So we don't want underfit. We don't want overfit. We want to be somewhere in between, right? So the theory behind is close to Vapnik theory. So it's based on this idea that you cannot get a good prediction of the expected loss function by taking it on the data set, because you don't have this kind of convergence. Okay, so if you try to look at the limit of this one, because M is based on the data set you have, you cannot use the law of large number. Okay, so this is not going to converge to this quantity. Okay, so you need to get a training and a validation sample, or something else. Maybe I can show you on some data set. Okay, so here I got a data set. So I'm just running so it's just a classification problem. Okay, so I got some blue points and some red points. I got a training sample and I got a validation sample. Okay, so we're going to train a polynomial regression model, a logistic model. Okay, so this is a linear model. So it's here we got the blue line, which is the rate of error we got on the validation sample, and the red one, which is on the training sample. Okay, so what we get is if we increase the degree of the polynomial, so maybe I will just end here. So what we have is we're going to get some very, very small areas because we got some red points. So we got accumulation of red points, so we want to capture that. Okay, so we're going to get a model which is going to try to capture this property. But when we get back to another data set, actually we don't need it, right? We should not get a lot of red points in this area. And this is why we got big error in terms of prediction, because we try to focus on areas where we should not have. So basically we start to predict the noise. Okay, so it's always this trade-off between the signal and the noise. We want a good model on the signal, but if we have a too complex model, basically we're capturing information about the noise, right? So this is this idea of complexity of the model. Okay, so we don't want to get something too complex, because if we do so, basically we're just capturing information about the noise. And this is clearly what actuaries want to avoid. Okay, so you don't want to put all the information about anything about where the people are living and so on, because you're going to capture something which is not the signal, which is not the true value, but it's something that is just pure noise. I think okay, I have to rush. Maybe I will skip most of the talk, actually. and try just to get to the conclusion, because I've been talking a lot of different things. I will, okay, I think I wanted to talk about a lot of things. Okay, I'm just going to end with two important things in terms of data. So basically, we will have the introduction and the conclusion. There will be a talk tomorrow about what's inside, so about the modeling issues. There is something that is becoming extremely important nowadays. It's the privacy problem we have in dataset. And just to mention one important thing about legal issues in the US, actually it came up with a problem with some insurance data. They got a very important problem, which is called the whale issue. It's related to the fact that there was a public insurance company that was pursuing health insurance for state employees. And because it was a state, somehow a state insurance company, they were obliged to provide data, okay, so to make them public. And they published data, so the GIC data set, they mentioned so it was supposed to be summarized data. Like they got the zip code, date of birth, the gender, and then a lot of things about those people. But it was supposed to be within different classes. So it was not nominative. So we didn't have the information about the name of the people. It was everyone with the same zip code, everyone with the same date of birth, everyone with the same gender. There will be one line in the data set. And it was compulsory. They were required to provide this kind of information. And then some researcher has been working with a voter data set where we got similar information, right? We got the name of the person they vote for, the zip code, the date of birth, and the gender, okay? And the thing is, when she started to look at the two data sets, what she observed is basically with those three information, the zip code, the date of birth, and the gender, almost 80% of the Americans are uniquely defined. So basically, they've been able to reach and to see, okay, this one was going to vote for that person. He had some big health issues. And they started to get some big problems. Like, he's been able to detect, to extract actually all the information, all the medical records for the former governor. And they started to say, okay, maybe we have some big issues about providing data. And it's really a big issue. So it's a problem of anonymity. Okay, so everyone now in companies are scared about this issue. So for researchers, it's a nightmare because previously companies were willing to give me data, like play with that, do something. And now they are very, very scared about this issue about anonymity. So it's something that is extremely important for us researchers to have individual data, but it looks like insurance companies are so scared that they can identify everyone. I mean, I don't care about the names. I don't care about a lot of information about the driver. I just care about how many claims someone got and additional information about experience and so on, but I really don't care about who this guy is. And it's very difficult to get data because actuaries have the feeling that they might go against the law if they give me some information. So it's something that is extremely important. And then to end up with something also very important for the future is what do we do with those models? So I would just mention, so a few years ago, like 10 years ago, with Michel Denuit, we published a book in France on mathematics of non-life insurance, and we got this model about the pure premium. Like, we got a very simple model with no segmentation. Okay, so everyone is going to pay the same premium, so it's the expected of the losses. So in that case, all the variability is kept by the insurer. The thing is, when you can have the true risk, okay, then you're going to split the risk, the variance of the risk, between the insurer and the insured. Okay, so we have this split of the variance, like the standard Pythagorean formula. So we're going to split the variance between the insured and the insurer. And when you have partial information, it's slightly more complex because we got part of the insured is going to get more variance because some part of the variance is coming from the fact that is missing information in this data set. Okay? So based on this property, we thought that there was some kind of property of spiral of segmentation. Like, the market will always go for more segmentation. Okay? So we had the feeling that companies will be looking for new data because it might help them to get a good pricing, and actually to get rid of the risk. Okay, so it's something that was what we expected, and then we started to work on a very simple model. Okay, so it was a model we wrote. So it was, assume that you got two variables. So it was a very simplistic theoretical model. You got two possible covariates, okay, and we got four models. Like the one was going to give the same price to everyone. The one was not going, so maybe there is a gender, and the other one is another one. So you got the one who's not going to use the gender, the one who's not going to use the other one, and then the one who's going to use everything. Okay, so you got the no segmentation model, you got two models in between, and you got the supposed to be perfect model. Okay, so if we think of what we do in statistics, we want to get the good model. Okay, so if you're in an insurance company, you want to get this one. You want to get the last one because if you think that you need some covariates, you try to get them. Okay, you try to get the larger data set you can get to get the best model you can have. But when we try to get them, when we put them in competition, what we got is basically this one as a good model, but a very small share of the market. Okay, so we got a company that is going to get, if you think in terms of Solvency II, they need a lot of capital because basically they got such a small share of the market that basically the loss they can get is huge. So it looks like in terms of solvency, a company with a not that good model actually couldn't perform very, very well. And this was what we got in terms of theory. And we've been playing with that. So last year we've been trying a pricing game in France. Okay, so we got a big data set with a lot of insurers. We got observation about losses. And I've been asking a lot of actuaries to give me prices. Okay, so I give them another data set. So we got 100,000 observation with losses. And I got something like 37,000 new clients, and I wanted to get a price. And then I use as a price maker. So we got different clients. I got different prices from different companies. And I've been playing like, okay, I'm going to choose the cheapest one. Okay, so this was a very simple model of market. Like insurers, they choose the cheapest one. Then I said maybe they just choose between cheap ones. Okay, so maybe we got 3 cheap price and it's going to choose randomly between the 3. And then there was something with like history on background. So what we end up, so I got like 14 insurers who played the game. Okay, so we can get very different shares. Okay, so some insurers got only 1,000 contracts. Some of them get 7,000 contracts, so from 1 to 7. The thing is, so it's not really sensitive to the way people choose their insurance company. Okay, so I will skip this part. But when we look at the loss ratio, we got very different results. Okay, so we can get companies. So the loss ratio was quite high. Okay, mainly because some insurance companies have been able to spot very no risky people. Okay, so they've been able to find some niches. Okay, but some companies got very, very high loss ratios. So what we got, so maybe I'm just going to go a bit fast, is basically that we got companies with high loss ratio. Maybe I can just get on those information. So this is what we got from GLMs. Okay, so we got some insurance companies working with GLM in mutual funds. So they got a loss ratio close to the market, okay, with some not that bad share of the market. And then we got actuaries working with gradient boosting. Okay, so they've been using some machine learning techniques. So what we got basically is they got a very good loss ratio. But basically what they do is they got a very small share of the market, and basically they're driving the prices down. Okay, so what we can see when we try to compare what can be done with machine learning and GLM is not only a statistical problem. It's really a choice of what you want to do with your insurance company. If you want to go deep into machine learning, you will get extremely low prices for some insured. You will get them for sure, okay, but then you will have a very small share. So here we don't have a dynamic game, okay, but I think that if you got a very small share of the market 1 year, it will be very difficult for the future to get prices for everyone, right? Because basically you use what you got in your portfolio to make predictions and to get models. So having niches is maybe nice to get a small loss ratio, but basically you're going to miss a lot of possible insured, and then you will not be able to price them in the future. While people with GLM, they got a more diversified portfolio, okay? They got a larger share, okay? And yes, they got a bad loss ratio, but I guess it's mainly coming from those people who are going to break the market by using those machine learning techniques. Okay, so when we try to look at what's going to happen if we try to compare standard econometric models and machine learning techniques, we end up with some kind of scary output in terms of what might happen in the market. Okay, so we got very a strong correlation between the loss ratio you got and the market share you get. Okay, so if you want a very low loss ratio, then you're going to get a very small share on the market. So it might have also an impact in terms of solvency. You're going to need more capital to be able to insure those clients. Okay, and just to conclude, so I just wanted to say that doing data science is something which is really a lot of fun. So we can do a lot of things with all those data we have, right? We can start looking at things that we were only thinking of a few years ago, okay? So we might have the information, we had the intuition that the more you drive, the more likely you will get a claim. So it was theoretical, but now with GPS we get data, right? We can confirm that to reality. And I mentioned this book by Nate Silver because it's exactly the problem we have, is try to distinguish the signal and the noise. And he got this quote I got this quote from this book, which is data will never talk. Okay, you cannot let the data talk because they will not talk, and actually we talk for them, right? We ask for something, and then they get it back. Okay, so it's a discussion with the data. Okay, we need to discuss with the data. We still have the background that we have been trained as actuaries, as economists. We got intuition about what might happen, what could be connections between losses and covariates. Data will bring us additional information. We can improve the model, but it's not purely learning from the data. We need to discuss with the data, and maybe we can do something with that. I guess I will end here. Thank you.
Thank you, Artur. There were two questions from the audience. One of them, you already answered that. It was from Mrs. Blanco from the Zurich Insurance Company, and she was asking about the difference between machine learning and GLMs when calculating prices, and you just answered to that question in the last part of your talk. What I'm suggesting, given that we are very, very tight on time, is that there is another question by Mr. Piulax, who is a PhD at this university, and who would like you to comment on the panel data analysis. And I suggest that you comment on that in your wonderful blog, and you give us the opportunity to visit that. So I would like to close the session, and thank you everyone for coming, and also thank you, Artur, for your very, very exhaustive talk. Thank you.